This particular section, they're mostly conceptual, but make sure that you understand the definitions, because if you don't understand the definitions or the vocabulary, then when you're presented a chart, you might get the you might put down the wrong information. So that's what I'm going to try and make sure that you understand in today's discussion. So let me go ahead and get started here and talk to you guys about kinetics. Okay, kinetics has to do with how fast the reaction proceeds. Okay, and when the reaction proceeds, it usually attains a state called equilibrium, which is the next topic after this. So chapter 10 covers both kinetics and equilibrium. So what you see here in this particular cartoon is a guy just sitting around and his car's getting rusted. And that's because rusting is a chemical reaction that happens to iron. And what you want to really do is not make that reaction go fast, but you want to slow down that reaction. So if you can control the kinetics of rusting, then hopefully you can prevent that, because when iron reacts with oxygen, then it breaks down the structure and the strength of iron and makes it weak. Iron oxide is weak compared to iron. So you want to slow down that particular reaction. So kinetics and equilibrium. Kinetics has to do with how fast you reach like the end of the reaction, but the end of the reaction is actually when equilibrium is attained. Most reactions, unlike what we learned in chapter 7, doesn't come to an end. What happens is that you get enough products that are built up in the reaction that some of the products start back reacting and combine with each other and forms the reactant, the starting material. Okay, so when the rate at which the product is formed is equal to the rate at which the reactant is reformed, you've reached equilibrium. And usually chemical reactions will attain that. And because the rate at which products form and the rate at which the reactant reforms are equal, it looks like the changes are not occurring, because if the product is forming at the same time the reactant is forming, then the concentrations will not change over that period of time. It looks like the reaction has stopped. So we'll look at that particular aspect when we get to equilibrium. But for now, just we're going to be talking about kinetics. So here's the chemical reaction of rust. Iron plus oxygen goes to iron oxide and some water. That's why you need moisture, and that iron needs to be exposed to oxygen. So if iron isn't, if it goes like it's exposed to water and it doesn't have a coat of paint or some oil to protect it from oxygen, then this is the reaction that will occur. That basically is rust. Okay, so another reaction that occurs, but you don't see it because of the kinetics factor, is graphite can actually convert to diamond, and diamond can convert back to graphite. And that difference in energy is not very big. But the reason why your diamond ring doesn't convert over to the lead of your pencil, to the lead of your pencil, which is graphite, by the way, not lead, is because of the kinetic barrier. Okay, that kinetic barrier is what we're going to be talking about today. So let's take a look at why reactions are favorable. Reactions are favorable because whenever a chemical change occurs, bonds have to break and new bonds have to form. Then and only then, when the atoms are rearranged to get a new chemical identity, do you have a chemical reaction. So anything that advocates, that accelerates bond breaking and bond forming, is going to speed up the reaction. Okay, so here it is again. Bond has to break, bond has to form, and then you get a chemical reaction. When you break a bond, you have to put in energy. Okay, When you put in energy to a reaction, it's called an endothermic. Endo means enter. So if you're going to, like if you've got something and you want to pull it apart, you got to put in the energy. So that means that if something comes together, that means that it has to release that energy. Okay, if in one direction you're putting energy to pry it apart, then in the other direction, when it comes together, it's releasing that energy. So think about that in terms of kinetics, because that's an important concept. So one's called endothermic, where you enter the energy. The other one's called exothermic, because the energy is being released. Okay, so these are vocabularies that you want to remember: endothermic and exothermic. So when you put in energy to a chemical reaction, then energy is a reactant, because the energy plus the ingredients, the reactant, goes to product. On the other hand, when energy is released, kind of like when you combust something, when you burn, say ethanol, you guys did this in your last experiment, you expose it to oxygen, you spark it, and then all this heat is released. Okay, that's energy being released. So we call that exothermic. Okay, and generally what goes on is that energy will be a product. Endothermic energy is a reactant. Exothermic energy is a product. It's being released. So there's there are reasons why reaction occurs, and that means that the chemicals have to combine. They have to collide in order for bonds to break. That's called collision theory. So in order for a reaction to occur, they have to first come together so that they can meet and form new products. And sometimes when they come together, they'll break the bonds upon each other. Sometimes when they come together, they form new bonds so that they form products. Okay, and so the greater the frequency by which they can collide, the faster the reaction. That's why if you're looking at how fast something dissolves, if you're looking at, say, how fast can I get this sugar to dissolve? If you put a sugar cube, and the sugar cube, it's a square, and the sugar that is exposed to the surface in that sugar cube are the only ones that's going to start dissolving first. Okay, but if you take that same sugar cube and smash it so that you have thousands and thousands of pieces, so now all the sugar molecules are exposed to water, then that'll dissolve first. Okay, so there's more collisions in that. The surface area is going to be greater when you smash it, and so you have more granular exposed to the water as opposed to a sugar cube. So that again has is a factor in terms of collision factor. Okay, then it's also got a, and you can't see this, but the chemicals got to align correctly so that the right bond breaks and the right bond forms in order to get your product. So that's called the orientation factor. And then finally, how hard they hit is something called the activation energy. It's not enough to just collide. Okay, they got to have collision enough to break the bonds, and so that is the minimum energy to get that reaction going. So we call that the activation energy. Activation meaning that that's the energy required to activate that reaction. So here's again collision frequency. They have to collide in order for these things. More particles, faster the reaction. Here is orientation. Okay, the orientation has to do with also called steric factor. They have to have the right orientation. Now, there's no way for you to monitor a chemical as it collides, so we treat this statistically. Okay, we said there's a certain statistic based on what we know that certain chemicals are going to combine and form products. So that's going to be called the steric factor. Okay, so and then of course the impact. They have to hit with enough energy so that they can break bonds and form the right one. So these are all factors that leads to chemical change. So when a reaction occurs, again, let me tell you about the energetics. When the product is lower in energy than the reactant, this is the case when you burn ethanol in your last experiment. Ethanol has a certain amount of energy. All chemicals have a certain amount of energy. But when it changes to a product, the product will have different amounts of energy. The products could be lower in energy or the higher in energy. Well, ethanol was the reactant that you guys did in that last experiment. And then when you ignite it with oxygen, you produce carbon dioxide and water. Carbon dioxide and water is lower in energy than ethanol. It's lower in energy than ethanol. So that difference in energy is actually got to be released, okay? Because like matter, energy cannot be created or destroyed. It's only converted from one form to the other. So in this particular case, we're converting chemical bonds, chemical energy to heat. And maybe if you hear some explosion or something, then that's energy being released. That difference in energy between the reactant and the product is the heat that's being generated. And so whenever you go down in terms of the energetics, you have a certain energy of the reactant, energy of the product, and you're going downhill where the product is more stable, less energy than the reactant, then that energy is released. That's an exothermic reaction. So that's the cartoon that you see right here. This is the energy of the reactant. We call that ER. This is the energy of the product. We call that EP. And the energy of the product is lower. That difference right there is called delta H, better known as enthalpy, or you can think of it as heat, the change in the heat. And because it's downhill, that is a negative value. It's a negative value because it's being released. Okay. Now, understanding the signs is going to be a little bit difficult. So I'm going to give you an analogy to make sure that you understand that exothermic means that the energy associated with that reaction is negative. Endothermic, again, you're putting energy. The energy associated with that reaction is positive. And here's here's the nomenclature for that. Okay, exothermic, delta H is negative. Energy is a product. Energy is a product. Now, what happens when you have a chemical reaction and you need to put in energy in order to get to the products? Okay, you got to pump in the energy for that reaction to occur. Well, that means that you're putting in the energy. Energy is a reactant, and then you make the reactant go to product because the product is higher energetically. Okay, so in that particular case, we say that heat is absorbed, energy is positive. It's called endothermic. Energy is a reactant. So let me just kind of review that real quick because that's an important concept. So in one case, we have something called endothermic reaction. And you think of endo as enter. And so the reactant plus energy goes to product. Okay, so that means that the reactant is here. This is the energy scale, and this is the product. So this is the energy of the reactant. This is the energy of the product. And what you need to do is you need to pump in this amount of energy. That's called delta H. And that delta H is positive because you're going from a lower to a higher. Okay, so that's positive. And exothermic, that's exit, EX, exit. So again, this is the energy scale. What you have is a energy of the reactant right here. This is energy. This is energy of the products right here. And that difference right there, you're going downhill, so that's negative. That difference right there is delta H, and that's negative because you're going downhill. So the way you want to think in terms of energy exchange is kind of like, the way I like to explain it is like you. If you were to take in some cash because maybe you won the lotto or you just got paid, then that's a happy thing. Okay, that's a happy thing. That's a positive thing. So money coming into your bank, that's positive. Okay, so energy going into the reaction, that's positive. Endothermic entering. On the other hand, if you have to pay bills or you have to pay for something else, that's a negative thing. Okay, because it's going to be exiting. So think of that in terms of money flow. When it comes into your bank, that's positive. When it exits your bank account, that's negative. Same thing with a reaction. In a reaction, if the energy is coming in to help that reaction occur, then that's positive energy. Delta H is positive. It's endothermic. It's endothermic. On the other hand, and energy is a reactant. On the other hand, when energy is released, and so you feel the heat, then that means that energy is a product. That's a negative delta H. By the way, when energy is released, just like in the last reaction, last experiment, you can feel the heat because the heat is being released by the reaction. On the other hand, if energy is absorbed, an endothermic reaction, it actually feels cold. And you guys should have seen that when you mix baking soda with vinegar and you felt that the energy actually dropped. That's an endothermic reaction. What's occurring is that when you feel something in which energy is being absorbed, the heat in your hands is actually being removed, being used by that reaction, and the removal of energy from your hands makes the molecules that are because the energy is being removed, makes the molecules in your finger move slower. That sensation feels colder. So an endothermic reaction, it'll feel cold. In an exothermic reaction, it'll feel warm. Okay, because in an endothermic reaction, the energy is being supplied by your hands, it's going into the reaction, and the lack of energies in your finger makes it feel cold. So that's something to think about when you're talking about endothermic and exothermic reaction. So here it is right here. Now, we've only looked at the energy of the reactant and the product and the difference, whether it's energy going up or energy going down. Let's talk about the kinetic factor. When you have a kinetic factor, okay, you need to supply a greater amount of energy. See this boulder right here? That boulder has a certain amount of energy based on potential energy. If that boulder was sitting on a cliff like that, and it's a certain height, then when you drop it, then that potential energy is going to convert to kinetic energy. Okay, and potential energy is energy storage. Kinetic energy is the energy of motion. And when it drops and right before it hits the ground, all the potential energy is converted over to kinetic energy. And so potential energy is equal to kinetic energy in that particular case. And so this difference right here is delta H. And because it's downhill, You see how this is the energy of the boulder? And so we call that energy of reactant. And this will be energy of the product. Because it's downhill, that's an exothermic process. But the reason why our reactant doesn't convert to product right away, I mean, ethanol does not spontaneously burn, okay? It just does not. You got to give it a little spark. The reason why chemical reactions don't spontaneously convert over to product is because of this little barrier right here called the activation energy. You first have to get over that barrier. Once you're over that barrier, then you have the green signal to move over to product. So you got to supply the chemical a minimum energy. That minimum energy allows that boulder to be on the top part of that activation energy. And then that boulder can either fall back or move forward. It can either return back to reactant or convert over to product. And so this is called the transition state. It's called the transition state. Okay, because it's transitioning from the beginning, the reactant, over to product, but it hasn't decided yet whether it's going to remain as a reactant or go to product. And this difference right here, that difference between where you start to its highest point, that's called the activation energy. You need that minimum energy just to get that reaction to go. Okay, you need that minimum energy in order for that reaction to go. Now, this right here is an exothermic reaction. It can also occur for an endothermic reaction. We can have a boulder that looks like this, okay? And then that would be the product right here. So you still need to climb this activation energy. The activation energy is still that hill that it has to climb, but now the energy of the product is this difference right here. That's delta H. Okay, so that would be an endothermic reaction. Why? Because the product, this is your product, is higher in energy than the reactant, so it's uphill. But you still need to pay a minimum price just to get it over that hill. That is called the activation energy. This is called the transition state. Okay, that's called the transition state. That's the very top. Now, this is the activation energy in the forward direction because we're moving in the forward direction. So we put that a cap with an F because we're going from reactant to product. But if we're going in the reverse direction, then that activation energy would just be where that particular reactant starts to the highest point. And so this right here would be the activation energy in the reverse direction. Okay, clear this real quick. That would be the E-act on the reverse direction because you're going in the reverse direction. Remember, I told you that reactions can go in the forward or the reverse. So if this reaction were going to the reverse, then that would be the activation energy in the reverse. And then you can see that an endothermic reaction in the forward direction is an exothermic reaction in the reverse direction. And that makes sense. If you take a look at A plus energy going to product, and that's the forward direction, then the reverse direction would be product going to A plus E, and now E is going to be on the product side. So if in one direction it's endothermic, in the opposite direction, it's exothermic. That's always the case. It's always the case. Okay. And usually it's rare in which the reactant and the products have the same energy. It's very rare, but it does happen by coincidence. Okay. In that particular case, the energy, activation energy in the forward is equal to the activation energy in the reverse. But in general, depending on whether it's endo or exo, the two activation energy, forward and reverse, are not equal. So think about that a little bit. Okay. And so let's take a look at this. This is an important chart because you guys will probably see this in your next quiz. Okay. Again, this is a reaction. This reaction happens to be this chemical converting over to this chemical. What's the difference here? The carbon and the nitrogen are switching places. You see how this is nitrogen in the middle and this is carbon at the end? Well, what's going on is called what we call an isomerization. You guys are going to learn that in organic chemistry, isomerization. That's where the carbon and the nitrogen, that's where the chemical formula is still the same. The atomic arrangements are different. So the formulas are the same in both these chemicals, but now the way they're attached to each other is different. So that makes these two chemicals isomers, The process of going from one isomer to the other, one structure to the other, is called isomerization. You guys are going to learn that in organic chemistry. So let's take a look at this and see how we can diagram these things. And this is important because what I will usually do is I will give you a chart, like in my next slide, and you guys have got to fill in the blank. Okay, and so let me kind of define these things for you so that you can fill in the blank correctly. This right here is the energy of the reactant. Okay, this will be an energy scale. That might be like 200 kilojoules to maybe 600 kilojoules. So wherever this thing lies on that energy scale is the energy of the reactant. That's a chemical species. A reactant is a chemical that you can isolate. So that has a certain amount of energy. This right here is another chemical species. That's your product. That's the energy of the product right here. This right here. So it's a value you can read in the energy scale. Okay, these are chemical species right here. Another chemical species, but is not, it's not, can't be isolated, but it exists as it goes from reactant to product, is this transition state right here. That's a chemical species. That's the transition state. So this right here would be the energy of the transition state. We call that E double dagger. The double dagger, see this double dagger here? It's that symbol is called a double dagger. That's the symbol for the transition state. Transition state. And again, that chemical is a species that is short-lived, but it's still a chemical species. So you can read that energy in the energy scale. So any chemical species, whether it's reactant product or intermediate or transition state, you can read their energy based on that scale. Now, this right here is the activation energy. That's a process. What is the activation energy in the forward direction? Well, the activation energy in the forward direction depends on two values: the energy of the transition state and the energy of the reactant. So the activation energy forward is equal to the energy of the transition state minus the energy of the reactant. So that's a difference. That's a difference. Okay. What's the energy in the reverse direction? The transition, the activation energy in the reverse is going to be the activation energy in the is the transition state, again, the highest point minus the energy of the product. It's this difference right here, that difference right there. So those are not chemical species. That's a process. Okay. Activation energy forward, activation energy reverse, that's a process. You have to do that calculation to get that value. And then what's the energy of the reaction? The energy of the reaction is just the difference. Let me clear this up for you. Between this and this, that's the energy of the reaction. We call that delta H. Okay. What is the change in heat? You can think of H as heat. Technically it's called enthalpy. But what is that? And you know it's downhill because the product's lower in energy than the reactant. So that's delta H. And again, that's a process. It's a calculated value. And it's basically delta H equals energy of the product minus energy of the reactant. So let me emphasize this again. Chemical species, whether you have reactant product, transition state, or intermediate, are going to be energy that you can read off the scale. Processes like the activation energy or the energy of the reaction is going to be a calculated value. And so you need 2 points. Okay, so what we've drawn here is a simple diagram in which the reactant converts over to product. Some reactions are multi-steps. Some reactions are multi-steps. Say we've got A going to an intermediate, and then the intermediate moving on to product. Okay, so it's a two-step reaction. The net reaction is this right here, A going to product. Why? Because the intermediate will cancel out when you add the two reaction. So the way you draw a reaction profile diagram for that is, this is the energy. This is energy again. This is A, and this is this energy. But A goes to I, an intermediate. This would be the intermediate right there. In order for A to go to intermediate, it has to undergo an activation barrier. Still has to undergo an activation barrier. That way A doesn't convert over to intermediate automatically. Reason why chemicals do not spontaneously change over to the product unless it has enough energy or to an intermediate is because of this activation barrier. It's basically holding that chemical back in order to convert to that second state. So this would be the transition state, E transition state 1. This would be the activation energy 1, because that's the first step. And this would be delta H 1, because that's the first step. Now, because this is a two-step reaction, then you also have a second activation energy, and now this is your product. So this right here would be, this difference right here would be E activation energy 2, because that's your second step. It's that mount that you have to climb. This is transition state 2, because it's the morphing of the intermediate to product. This right here would be the energy of the product. And this difference right here would be delta H2. Okay, that's delta H2. So you treat each step as its own reaction. Reaction 1, reaction 2. But when you're looking at the overall reaction, what you see in the overall reaction is where you start and where you end, as well as the highest point right here. Okay, so if you're looking at the overall reaction, no matter how many steps you have, then the energy, activation energy for the overall would be where you start to the highest point, the highest transition state. That would be activation energy over forward. Okay, and then this would be the energy of the product. And then you don't worry about the intermediate. This right here represents that green line. But if you're looking at the individual steps, A going to I going to P, then the first step has an activation energy. It's got an initial transition state. It's got a delta H1. The second step has an activation energy forward. It also has an activation energy reverse. It's got a delta H2, the difference in energy between the intermediate and the product. Okay, and you have an energy of the intermediate and energy of the product. But if you're looking at the overall energy, then you ignore the individual steps and you just look at overall. And the overall is the energy at the beginning, the highest point to the product. And I can fool you and do this. Let me clear this for you. I can do this. I can do this. So here's your energy of the reactant, and basically do that. And this is energy of the product. And the activation energy overall, if I ask you what's the activation energy overall, a lot of students will do this. Don't. A lot of students will do this. They'll add this activation energy, and they'll add this activation energy, and say that's the activation energy overall. No, don't do that. And the reason why you don't do that is because you're not worried about the steps to get the product. All you're doing is you're looking at the overall This is the highest point right here. This is where you start. It doesn't matter that you have an intermediate that's lower. This would be the activation energy overall. E-act forward overall. You forget about the middle, okay? But if you have multiple steps, you can calculate the energy of the reactant, energy of the intermediate, the activation energy for that first step, and the transition state of each step. This would be the transition state 1 right here. E transition state 1 for the first step. This would be your intermediate, and this would be transition state 2. Transition state 2 is the highest. So that's the energy that you would use and the energy of the reactant to calculate energy activation overall. Okay, activation energy overall would be the highest minus where you start. You forget about the details in the middle. So hopefully that's clear. And so this is just one step right here, but you got to understand how one step works if you're going to be able to answer the questions that I give you here. Okay, so if you take this reaction and these things were blank, or I give you this diagram and I ask you what's the energy of the transition state, all you got to do is read this. That's 50 kilojoules, because that's transition state is a chemical that exists. Okay, so you just read that off this scale right here. That's 50 kilojoules. What's the energy of the reactant? It's right here. It's where you start. That's 20 kilojoules. What's the energy of the products? Right here. That's 10 kilojoules. So you're just reading it off the chart. What is the energy of the reaction? The energy of the reaction, also known as delta H, is the product, which is 10 minus 20. So that's minus 10 kilojoules. Notice it's downhill. It's negative. It's exothermic. It's exothermic. It's always, whenever you're looking at a difference, delta, it's always the final minus the initial. It's always the final minus the initial. If you're looking at delta T, the change in temperature, it's the final temperature, the last temperature minus where you start, final minus initial. So this right here is final energy 10 minus initial energy 20. 10 minus 20 is minus 10. What's the energy of the activation forward? That'll be 50 minus 20, that's 30. It's positive. All activation energy, by the way, are positive. It has to be up. Okay, there's no such thing as a negative activation energy. No such thing. Okay, what's the energy, activation energy in the reverse? This is the activation energy in the reverse. E-act reverse. So we're looking at 50 minus 10, that's 40. Okay, you still have to climb 40 kilojoules to get to the top of the hill. Here, you've got to climb 30 kilojoules to get to the top. It's always positive. Activation energies are always positive. So that's your answer for this. Okay, that's your answer for this. And that's what you see in this chart right here. You should see this in terms of your answer. Actually, let me go back. Yeah. Okay. So that's the calculation we have. Now for an endothermic reaction, this is an endothermic reaction. You guys should be able to figure out what is the transition state energy. That's this right here. What is the energy of the reactant? What is the energy of the product? What is the activation energy in the forward direction? What is the activation energy in the reverse direction? What is delta H of the reaction? And so you can just calculate these or read it off the scale. And so that's 45 is the transition state. Okay. So why this thing's not working? Oops. 20 is the energy of the reactant. 25 is the energy of the product. 5 is the positive 5 is the delta H of the reaction. 25 minus 20 is positive 5. The forward direction is 45 minus 20, that's 25. And the reverse direction is 45 minus 25, that's 20. Okay, so make sure you understand the vocabulary associated with that, because you're going to need to be able to read the chart and then figure this out based on the chart like that. Now, what is the other factor that is responsible for accelerating the reaction? By the way, let me go off on a tangent and let me show you something here. This is the energy of your reactant. And this is an endothermic reaction. This is the energy of your product, okay? And the question is, if you raise the temperature, why does the reaction go faster? The reason why when you raise the temperature, the reaction goes faster is because if you have reactant, some reactant are going to have low energy, some reactant are going to have fast energy, even at a certain temperature. There's something called a average energy at that temperature for the reactant. So they don't all have the same energy. Some are slow, some are fast, but the average is this right here. This is the average energy. And let's say that is 25 kilojoules. Some will have lower than 25, some will have slightly higher than 25. And what's going on is that their average is 25. Now, what happens when you raise the temperature? Well, when you raise the temperature, then the average energy of those chemicals will be higher. And so when you get a higher population of that chemical, then there's going to be more chemicals of the reactant that can now surpass that activation energy. So what you're doing is you're changing the population of chemicals that will overcome that activation energy at higher temperature. And so if you can increase the population of chemicals that can overcome that activation energy, then you make the reaction go faster. You do not change that transition state. That transition state is still the same. You do not change the delta H of the reaction. That delta H of the reaction is faster. You just change the population of chemicals that can now have the minimum energy to overcome that activation energy. You change the population and you make that population bigger. So now it's going to translate to a faster reaction. That's what happens when you change the temperature of a reaction. Now, what happens if you add a catalyst? Well, when you add a catalyst, what actually occurs is the following, okay? When you add a catalyst, let me draw this again. You actually change the path by which this is the energy of the reactant, this is the energy of the product, and this is your diagram. When you add a catalyst, you cause that reaction to migrate to a different path. And because it's a different path, then the activation energy can be low. The activation energy can be lower like that, okay? And since the activation energy is going to be lower, then there's going to be more chemicals that can surpass that activation energy. There's going to be a faster reaction. So a catalyst is the only thing that will change the transition state and change increase the speed of the reaction, because now that transition state is slower. Changing the temperature doesn't change the transition state. It just changes the percent of chemicals that can overcome that activation barrier. Adding a catalyst lowers that activation barrier. There's now more chemicals that can overcome that barrier and move on to product. That's why it's faster. That's what a catalyst does. So let's take a look at this right here in terms of what happens when we have a catalyst. Right here, we lower the activation energy, the reaction is going to go faster. And that basically is because you have a different path to the product. Okay, so that's kinetics. That's kinetics in terms of that particular section in your book. Okay, hopefully it makes sense. Hopefully you understand that. Make sure you understand these diagrams, because these diagrams are going to be important for you guys to see when you have that question. I don't know why this thing's not working. It's probably my connection here. Okay, let me do this real quick. So again, that would be the take a look at the notes in terms of that. Yeah, you can see how the summary for that. Let me next move to equilibrium. Okay, let me next move to equilibrium. And equilibrium is yeah, that's the summary equation. Conditions for increase the reaction, nature of the chemicals, concentration, more chemical surface area, temperature, and the catalyst. Those are factors. So let's take a look at equilibrium. Okay, so equilibrium has to do with efficiency of the reaction. So let me start with that. Whereas kinetics tells you how fast you get to the end, equilibrium tells you how efficient your reaction happens to be. And so let me sort of illustrate this with a diagram. Okay, let's say that we have a reaction and it goes to product. And let's say that we have 100%, 100 moles of reactant. And in the process of going to product, okay, 70 of it converts over to product. In the end, what happens if 70% of it converts over to product, that means that 30% of it is still the reactant. Okay, so this will be 30 if it's only 70% is converting. So we have an efficiency there of 70%. Okay, and we're going to have something called an equilibrium constant, K equilibrium, that tells you this is only 70% efficient. Okay, K equilibrium is a constant. It's an indicator of how efficient that reaction is. Suppose we have another reaction, and let's say we have 100 here, that's your start, and 0 products, but at the end, let's say that you still have 70 here, and only 30 converts over to products. So we're going to have an equilibrium. This is a 30% efficiency. And we're going to have a K equilibrium reflecting that 30% efficiency. It's going to be a smaller number. K equilibrium can never be negative, but it can be very small or very large. It tells you the efficiency. Okay, so K equilibrium is a number between 0 to infinity, but it's never negative. So that's the way we measure efficiency of the reaction, and that efficiency is based on equilibrium. Okay, so let's convert that. So let's take a look at this right here. When something dissolves, okay, so this is a let's say it's table salt, NaCl, solid, and we're dissolving it to Na plus Cl minus, aqueous. When something dissolves, like table salt, when it goes into solution, what happens at the surface of that salt is that the water comes in and it's called hydrate. It stabilizes those ions and then dissolves it. Okay, if you have enough table salt in there, it'll start to dissolve, but then it'll hit a saturation point where none of the salt will dissolve any further because there's not enough water to dissolve it all. All the water is already tying up the ions. But what in reality is going on is that some of the ions in your table salt are actually being dissolved by the water, and some of the ions that is dissolved by the water is precipitating out. It's forming a product. So when those two rates are equal, the rate at which the table salt dissolves and the rate at which the ions recrystallize, that's equilibrium. That's equilibrium. Equilibrium does not mean that your reactant and the product are equal. Equilibrium means the rate by which your reactant converts to product and the rate in which your products convert back to reactant, that's equal. But equilibrium does not tell you that the chemical mass or the chemical moles of your reactant and product are equal. That's not equilibrium. Only that their their change, their formation are the same. And so it looks like nothing's happening. Okay. If you are replenishing a chemical as fast as it's disappearing, then it looks like it's constant. Okay. It looks like it's constant. That's the equilibrium process right there. So and that equilibrium process is called K equilibrium. Okay. That's an indicator of efficiency. So the way I like to view equilibrium is this concept of the teeter-totter. Now, when you have a teeter-totter or a seesaw, or even a balance like you see here, when the heights are the same, we say it's a state of equilibrium. But again, I want to emphasize to you, it's very important that you understand, equilibrium does not mean that the reactant and the product are equal in value, only that their exchange are equal. That the rate in which the product form and the rate in which the reactant reforms are equal. That's equilibrium. But I want to use this analogy because equilibrium requires you to understand that concept at a deeper level. Okay. And that's what's going to phase you in terms of these types of questions. But if you understand the seesaw analogy, then you can answer these questions that you are going to see in chapter 10, equilibrium. So the way I like to see it is that if you have a reactant going to product, you can force that reaction to produce more product. Okay. And the way you can do that is you can upset the equilibrium. You can upset the equilibrium by forcing that reaction to convert to product. On the other hand, you can force the product to return back to reactant. And each time you force that reaction to form more product or more reactant, when it finally ends, it's actually reaching a new equilibrium. Okay, it's actually reaching a new equilibrium. So let's take a look at this right here. This movie right here shows you that the rate in which the reactant forms product is equal to the rate in which the product returns back to reactant. We're at a state of equilibrium. And so we designate that by this double arrow. This double arrow tells you you have an equilibrium. The E on the reactant side tells you this is an endothermic reaction. This is an endothermic reaction. Energy is a reactant. Delta H is positive. Okay, you learned that from kinetics. And then this is an equilibrium reaction where dinitrogen tetraoxide forms nitrogen dioxide. But you form two nitrogen dioxide for that reaction to be balanced. Okay, and what you have here is this movie that is not working. Let me see about this right here. See if I can get this movie to work over here. Okay, so that you can see this and appreciate it. Let's see. And that would be okay. Let me find that real quick in my let's see. That would be over here. And again, I want you guys to appreciate this. That's the reason why I want to show this movie. is because it's an important concept, this equilibrium. In fact, it's the main section in the second part, understanding equilibrium. So let's see about this right here, this lecture notes, and see, where's that movie? That movie is not here. Okay. Sorry, my notes are not organized. This movie would just simply show you that what goes on is that N2O4 and NO2 are at an equilibrium. And if you put in energy, you can actually force this equilibrium to favor more product. And what you will see is that what you will see in this particular reaction is that this is the reactant, this is N2O4, this is the product NO2, okay? If you add energy to this particular reaction, okay, then it'll form more NO2, but if you cool it down, it'll form N2O4. So that's why you see this beaker. One is in warm water, the other one is in cold water. And what you're doing is actually controlling which direction this reaction is proceeding, either more product or more reactant. And that's based on the principle of Le Chatelier's principle, which is what we're going to be talking about in this particular section. Okay, so let me go ahead and move on from here. Okay, let me go ahead and do this. Let me go to this right here because it seems like my iPad's not working very well. Okay, so we have this. So let's take a look at the generic reaction. A plus B going to P plus Q. That's a generic reaction. Okay, it could easily be a reaction in which NH3 or N2 plus H2 goes to NH3. Okay, when you balance this reaction, then the small letters here, A, B, P, and Q are the coefficient of that balance reaction. Why is that important? The reason why that's important is because you can get an expression for K equilibrium, which I said was the efficiency of this reaction. And the way you do that is this, let's see about doing this right here. Okay, we try and do it this way. So if we have this reaction, then K equilibrium is going to be the products divided by the reactant. It's the ratio of products over reactant, but more specifically, it's going to be the concentration of P, and you guys know how to calculate concentration because we covered that in the last section, in molarity, moles per liter, concentration of P taken to the P power. See this coefficient right here? That's, you raise it to that power. Concentration of Q taken to the Q power divided by concentration of A taken to the A power, concentration of B taken to the B power. When you have all these concentrations and you use this expression, then you have that equilibrium constant. Here's an example. Suppose I have hydrogen plus nitrogen producing ammonia. The first thing that you need to do to that reaction is you need to balance it. So to balance this equation, I need 2 nitrogens right here. That means I've got 3 hydrogens right there, and that would be a balanced equation. There's a 1 in front of that nitrogen. So now you know the coefficient. The coefficient for hydrogen is 3, the coefficient for nitrogen is 1, the coefficient of ammonia is 2. So K equilibrium for that reaction is going to be equal to the concentration of ammonia. Whenever you have a bracket around a chemical, that means it's a molar concentration moles per liter, taken squared. Why squared? Because the coefficient is 2. Divided by the reactant, concentration of nitrogen to the first concentration of hydrogen cubed. That would be the mathematical expression for K equilibrium for that reaction. And if you have the concentrations at equilibrium, all you got to do is plug it in there, square the ammonia concentration, cube the hydrogen concentration, you divide it based on that, and you will get the efficiency, the K equilibrium for that particular reaction. Okay, so to get the K equilibrium value, you need the balance equation. You need the balance equation, and then you can put it in this form. Okay, so that's what we see right here. And again, I apologize for that because my font didn't come out clearly here. This would be products raised to the P power, Q raised to the Q power, B raised to the B power, A raised to the A power. These are your products. These are your coefficient right here. These are your reactants. And this is equal to the K equilibrium. So for any generic reaction, that's the case. Okay, I do need to forewarn you, however, okay? And the reason why I need to forewarn you is because of this concept right here. If I have a solid, let's say I have a solid NaCl, solid, and I change that to half its value, 1/2 of that, okay? Then if I have, say, 1 mole of NaCl, and now I have 1/2 mole of NaCl, then the volume would also be half, won't it? Okay, if you take a certain amount, like 1 gram, and now you have 1/2 gram, that volume will also be half, because the volume tells you how many particles you have. Well, the moles over the volume in liters, that's molarity. Okay, but now if you have 1/2 the moles and 1/2 the volume, isn't that concentration still the same? Because you're reducing both the moles and the volume to half its original. What I'm trying to tell you is that the concentration of a solid is going to be constant no matter what. Okay, the concentration of a solid is constant no matter what. Why is that important? Because only those chemicals in which concentration changes are allowed in the mass action expression. Solid, concentration is constant. If you have a liquid, let's say I have a glass of water here, and now I have 1/2 a glass of water, okay? Well, you got 1/2 a mole, that volume is also 1/2, so the concentration of a liquid is also constant. The reason why that's important is because when you write the mass action expression, you can only write chemicals in which concentration changes. That means solids, if you look at the phase in your reaction, and liquids do not belong in the mass action expression. They do not, because it's constant. Only gas and aqueous are going to be in the mass action expression, okay? Because that can change because of the volume. When you have a certain amount of chemical that is dissolved, and then you evaporate the water, the amount of chemicals there are still the same. The solvent has changed, and so the concentration is higher, so you can change the concentration. For solid and liquid, you can't do that. For gas, you can. You can take a gas and put it in a smaller volume, and so the concentration changes. The moles are not the same, but the volume has changed. That doesn't happen for solid or liquid, okay? So why is that important? Because let's take a look at this reaction right here. What I want to ask you, what is the mass action expression? That's products over reactant. You would write this: K equilibrium is equal to the product, carbon dioxide, okay, concentration of that, divided by reactant, and these are the two products, CaO, okay, CaO divided by reactant CaCO3. But these are solids. These are solids. So the concentration is constant. So you don't write that in the mass action expression. The K equilibrium for this reaction is just equal to the concentration of carbon dioxide. Or you can do it this way. K equilibrium equals the partial pressure of carbon dioxide if carbon dioxide is a gas. Okay? So only chemicals that are gas or aqueous are allowed in the mass action expression. And that's what you see right here. That's what you see right there. Okay? Because solids have constant, they don't change over time. When the reaction proceeds, let's look at this again because this is somewhat important. When the reaction proceeds, let's say that I'm forcing this reaction to move in the forward direction. I'm manipulating it so more chemicals being formed. So I'm saying that the reaction shifts in the forward direction. The concentration of calcium oxide doesn't change because it's solid. Concentration of calcium oxide doesn't change because it's solid. The concentration of carbon dioxide is going to change because let's say that that reaction happens to be occurring right here in this container. So calcium oxide, calcium carbonate, and calcium carbon dioxide. So your moles of carbon dioxide is increasing, but the volume is fixed. That means that the molarity is going to increase. But because calcium carbonate is a solid, then they're going to be their own volume. Okay, they're going to be their own volume. It's not going to be dependent on the size of the container, unlike aqueous or gas. Okay, now when we move this reaction in the forward direction, the moles will increase for calcium oxide, it will increase for carbon dioxide, and it will decrease for calcium carbonate. The moles, if this reaction was going in the forward direction, because it's going in the forward direction, the amount of calcium oxide will increase, the amount of carbon dioxide will increase, the amount of calcium carbonate will decrease. But the concentration for the solid doesn't change. That's important. The amount will change, but their volume changes proportionally. You got to make sure you understand. Okay, when it's going in the forward direction, the moles for the product will go up, the moles for the reactant will go down. When it's moving in the reverse direction, the moles of the reactant will go up, the moles of the product will go down. But for a solid and a liquid, the concentration does not change. The moles can change, but the concentration does not change. And what goes into the mass action expression? Only concentration or partial pressure. Only concentration or partial pressure. So concentration and partial pressure, well, that's a function of moles, okay, defined by the volume that it's contained. But for a solid and a liquid, that's defined by the mole, but it's based on its own volume. Its own volume. It's independent of what it's in. It's going to either grow in volume or shrink in volume, okay, for solid and liquid. So therefore, the concentration doesn't change for solid and liquid. Therefore, it doesn't go into the mass action expression. Doesn't go into the mass action expression. So please remember that, because that's an important concept, especially when you are trying to apply the rules of Le Chatelier, okay, when you're applying the rules of Le Chatelier's principle. So let's take a look at this reaction right here. Okay, this is the Haber reaction. This is the reaction I showed you earlier. And what's happening is that initially you just have nitrogen and hydrogen. So initially you just have you've got a certain amount of nitrogen and hydrogen. This would be your hydrogen. This will be the nitrogen right here. Okay, so you've got a reaction. You're going to put nitrogen in here, and you're going to put hydrogen in there. And for every one nitrogen, 3 hydrogens are going to be used up, and then it's going to form NH3. That's your product. And the balance equation would be 1 nitrogen for 3 hydrogen to produce 2 ammonia. So if we were to monitor what goes on to the concentration of nitrogen, hydrogen, and ammonia over time, or we look at the pressure of nitrogen, hydrogen, and ammonia over time, then we will see that the hydrogen will decrease because it's being consumed. We will see that the nitrogen will be decreasing because it's consumed. We will see that ammonia will be increasing because it's being formed. And then it looks like the concentration just stays constant. And that's what you see right here. Okay, you see this right here. I'm going to erase that. You see this right here in which the concentration just stays constant. Now, at that point, the reaction hasn't stopped. What's going on is you've now attained equilibrium. You've formed enough products so that now the products can back react and reform nitrogen and hydrogen. So now you're at equilibrium. So where the concentration doesn't change, that's the equilibrium time. That's the equilibrium time. Let's say that that time is 20 minutes. Well, before the 20 minutes, the reaction is still moving in the forward direction. After the 20 minutes, the reaction looks like it stopped, but now we've attained equilibrium. If you were to take this concentration, let me clear this right here. This concentration right here, this concentration right here, and this concentration right here. If you were to read that concentration and put it in the mass action expression, so the nitrogen looks like it's going to be about 0.65. That would be your hydrogen. The nitrogen looks like it's going to be about maybe 0.30. That's your nitrogen. Okay, again, I'm just reading this on this scale. The ammonia is going to be somewhere about maybe 0.4. Okay, that's how you would calculate the equilibrium constant. Just get those concentration, because now you're at equilibrium. Equilibrium constants are only those values when you reach equilibrium. It's not at your start, it's not in your middle, it's at equilibrium. It's at equilibrium. And then the other thing that you got to remember is you got to raise it to its coefficient. We have a 2 right here. We got to raise this to the 2 power. We've got a 3 right there. We got to raise this to the 3rd power. And we've got a 1 right there. That's just taking 0.30 as is. So don't forget to raise the power of those concentration based on the coefficient. So if you take this now and take 0.65, cube it, multiply it by 0.3, and then divide that by 0.4 and square it, then you will get the equilibrium constant. Then you get the equilibrium constant for that particular value. And so if I did that, okay, let's see if I have my calculator so that you guys can try this. Okay, reached my calculator. Hold on. Gotta find my calculator here. Okay, let me use my phone here as a calculator. Okay, so let me do this for you. I'm going to take 0.65 and cube that, and that's going to be 0.65 times 0.65 times 0.65. That will be, where's that function in my calculator? Okay, let's do this. 0.65 times 0.65 times. So 0.65 cubed is 0.274. So let me change that. 0.274 or 2.275. That's 0.65 cubed times 0.3 divided by 0.4 squared. That's 0.4 squared is 0.16. Yeah, 0.16. And so that right there is going to be 0.515. That's your answer. That would be K equilibrium. So K equilibrium basically tells you that the efficiency of this reaction, products over reaction, it's about 50-50. 50% product, 50% reactant. It's 0.515. Okay. If it was like a very big number, it's mostly product because these are your products, right? Sorry, that's backwards. You guys should have spotted me here. I got this thing all backwards because products are at the top, reactants are at the bottom. So this is actually reverse. Okay, this is actually reverse. Products is on top, K equilibrium equals products over reactant. So I've got this reverse. This is actually 0.40 squared divided by 0.65 cubed times 0.30. So I'm just going to take my answer, 0.5, and take the inverse of that, and that would probably give me the correct value. Okay, so that would be 1.94. So this is not it. This is 1.94. Try that again. 0.4 squared divided by 0.65 cubed divided by 0.3. Yeah, 1.94. That would be K equilibrium. That would be K equilibrium. Make sure you know how to do that calculation. It's not difficult. You just have to make sure you know how to pull the information from that. Okay. Let me move on. So in this particular case, like I said, this is the mass action expression. Excuse these right here. These things should be gone. Okay, my font kind of messed up. So this is basically P raised to the P power times Q raised to the Q power divided by A raised to the A power times B raised to the B power. It's basically products over reactant. Okay, and this number is going to be a number that is greater than 0, but never negative. And it's a number that could be very, very large if this number relative to this number is large. So when you have more products than reactant, then that number is much greater than 1. Okay, much greater than 1. Like 10 over 1 equals 10. Okay, so that means your product is 10 times greater than the reactant. 1,000 over 5 is greater than 1. So when your product dominates the mixture, because what happens is that when you have a reaction and it's contained in a reaction vessel, you have both chemicals present in that reaction vessel. The population of the product is going to be bigger than the reactant when the K equilibrium is large. When the K equilibrium is small, then the population of the reactant is going to be way bigger compared to the product. So you can see that when I give you an example, like let's say I've got 1,000 to 1. That's 0.001. That value is 0.001. So when you have an equilibrium constant that's much, much smaller than 1, never negative, it means that the reactant dominates that mixture. When you have a K equilibrium constant that's much, much bigger than 1, it means the product dominates that mixture, but you're still at equilibrium. Remember I told you, equilibrium does not mean that you have equal amounts. It just tells you the efficiency of that reaction. If it's much, much bigger than 1, you've got more product than reactant, but you're still hitting equilibrium. If you've got a number much, much less than 1, 0.0006, or 1 times 10 to the minus 20, your reactant is much higher than the product, but again, you've reached equilibrium because you have an equilibrium constant. If you've got an equilibrium constant, you've reached equilibrium. Okay, so that's what I want to illustrate here. And that's what you see right here in terms of this particular, let me erase this right here. When K equilibrium is greater than 1, then the product is greater than the reactant. When K equilibrium equals 1, they're about the same. When K equilibrium is less than 1, 1 times 10 to the minus 30, 0.007, much less than 1. Then the reactant is greater than the product. Okay, so again, K equilibrium is an indicator of efficiency. When the number is huge, you're very efficient in forming product. When the number is small, you're very inefficient in forming products. Most of it is a reactant. Okay, so that's what we mean right here. And you can calculate K equilibrium by, again, putting the concentration at equilibrium in something called the mass action expression. The mass action expression is the function of the balance equation. Leave out solids and liquids. Leave out solids and liquids. They don't belong in the mass action expression because the concentration is constant. Concentration is constant. Okay, so K equilibrium can be expressed in many ways. Sometimes we call K equilibrium Ka, Kb, Kw, Ksp, Kf. The different subscript just tells you the type of reaction. It's only providing you information. Is that reaction acid-base? Well, we call K equilibrium Ka. Is that reaction an acid? We call it Ka. Is that reaction a water breaking apart? We call that Kw. Is that reaction a solid dissolving? We call that Ksp, solubility product. Is that reaction formation of a product? We call that Kf, but it's still K equilibrium. These different letters down here just tell you more information about the type of reaction we are discussing. Okay, so don't let those letters intimidate you. As long as you see the K there, it's a K equilibrium. Sometimes we'll have a Kc and a Kp. Kc means that your mass action expression is expressed in molarity. Kp tells you that your mass action expression is expressed in atmosphere. Okay, partial pressure. And let me do this. You guys remember PV equals nRT. You guys also remember that molarity equals moles per volume. Okay, so this is for gas. This is for aqueous. You're going to see that gas can have a molarity. If you have a gas and you have a container, you can have molarity. And that's because this is moles and this is volume. So we rearrange this equation. So what we have is N over V RT equals P. Okay, that right there is molarity. That right there is molarity, moles over volume. All we've got to do now is remove RT, and we can remove RT by dividing RT by both sides. So molarity for a gas is equal to the partial pressure over RT. That's why we can say that if we know the partial pressure of the gas, we can also calculate its molarity, and that's why they can go into the mass action expression, because they're related. Solids and liquids cannot go in the mass action expression. But for a gas, you can take a gas and get the molarity for that gas based on its pressure, R and T. Remember, R is 0.08206, and T is the absolute temperature in Kelvin. It always has to be in Kelvin. You guys learned that in chapter 8, gas laws. So I want to make sure that you understand that in terms of that. Let me try and get to this right here, because I really want to talk to you guys about something called Le Chatelier's principle. This is the last concept I want to talk about. This is probably the most important concept of the section. Okay, Le Chatelier's principle. Le Chatelier's principle simply states that if you have to have a reaction at equilibrium, it has to be at equilibrium. You can't have the beginning. Okay, it's got to be at equilibrium, like at the end where the products are converting to reactant and reactant converting to products at the same rate. So if you have a reaction at equilibrium and you apply a stress, You can apply a stress by adding more chemicals or removing chemicals. So that's, you're upsetting the equilibrium. In other words, you're upsetting that mass action expression. Well, according to Le Chatelier, when you upset a reaction at equilibrium by either adding a stress or causing a deficit, the reaction will self-adjust. It will self-adjust until a new equilibrium occurs. And guess what? When that new equilibrium occurs, the concentration will have manipulated itself so that the products over reactant is equal to the same equilibrium constant as previous, before it was disturbed. That's the amazing part about equilibrium, is that you have an equilibrium constant. You know what it is for a certain temperature. Now you remove chemical or add more chemical, the reaction self-adjusts. And then when you reach the second equilibrium, if you take all the concentration and put it in the mass action expression again, it's going to be equal to that first equilibrium constant that you messed up. That's why it's called an equilibrium constant, because it's constant no matter what you do to the reaction, except if you change temperature. If you change temperature, all bets are off. The temperature will cause that equilibrium constant to change, but that's the only thing that will cause that equilibrium constant to change. Changing the size of the container, adding more chemicals, removing chemicals, will not change that equilibrium constant, only temperature. So that's what Le Chatelier's principle allows us to predict. Okay, this is basically it. And what are the changes that can occur? We can change the concentration. Okay, we can change the pressure. We can change the temperature. Temperatures like adding energy. And depending on what we do to that reaction at equilibrium, we can predict which way the reaction is going to favor. It's either going to shift to the right, more products, or shift to the left, more reactant, until a new equilibrium is achieved. That's the key. The reaction will initially adjust itself, and it'll cause more products to form or more reactant to form, depending on what the stress is. And then at the end, if we look at those concentration and plug it back into the mass action expression, they've magically adjusted so that they equal to K equilibrium again. Okay, that's Le Chatelier's principle for you. So the best way to understand this is this teeter-totter principle. Okay, so what really is going on? Let me try and explain this in terms of a chemical view. Okay, in terms of a chemical view, you've got A in equilibrium with B. Okay, and so you have a concentration K equilibrium, and these are both in the aqueous phase, in which B over A equals the equilibrium constant. Now suppose we decide that let's say that this is B right here and this is A right here. Now suppose that we add more A, so we've upset the equilibrium. So when we add more A will go up, and this ratio will not equal to K equilibrium anymore. It will not. The only way for this ratio to equal that K equilibrium is that even though we introduce A initially, A has got to be consumed. When you put in more A now has got to decrease in the course of changing itself, and B needs to increase so that you can form that new equilibrium. So by adding more reactant, we're forcing the equilibrium to favor more products until now the concentration has adjusted itself so that that ratio equals K equilibrium. Okay. That might be best seen by this analogy that I'm going to show you right here. Okay. Let's say that you've got A and B, and let's say that they are at equilibrium. They are at equilibrium. And again, I want to emphasize again and again, that does not mean they're equal. It just means that the rate at which they're changing are equal. But for our purpose here, we're saying that equilibrium is when these two are level. Now, let's say that we introduce more chemical A here. So we load up one side with more reactant. How does that upset the equilibrium? Well, it's going to upset the equilibrium because what goes on is that now that we've loaded up that side, this is what the scale will do. Okay, it'll tip over to that side, make that side heavier, and make this side lighter. Okay, the A side will get tilted down because there's more there. You're not at equilibrium anymore. You're not at equilibrium anymore because you've upset the system. But the system self-adjusts. The system self-adjusts. And the way it self-adjusts is that it'll take some of that A and convert it over to products. That's why what you see is that initially when you spike the reaction with a reactant, you will see more products being formed, because what will eventually occur is that as more products form, okay, more products form, then this thing goes back to balance. It goes back to balance. And so we can say that in order for equilibrium to be reattained, the reaction has to favor the forward direction. A has to get converted to B. A has to decrease in concentration. B has to increase in concentration until we get a new equilibrium. That's the teeter-totter analogy that I like to use in my discussion. And that's what you see right here. Right here, okay? We've got an equilibrium process. We load one side with reactant. How do we get back to equilibrium? We get back to equilibrium by taking that excess and converting it over to product. By converting it over to product, we say that the reaction shifts to product. So we say RSR. You see that reaction shifts to product, RSP, not RSR. Or the reaction favors products, or products are favored. That's all saying that the reaction is moving in the forward direction. Why? Because you put an excess on the reactant. It's got to get rid of that. The only way it's going to get rid of that is make more products, and until you get a new equilibrium. So whenever you're adding a stress, it's got to remove that stress and put it on the other side. Okay, it's got to put it on the other side. So you're able to predict, or you're able to manipulate the reaction to favor one side or the other depending on the stress that you apply. Okay, let's take a look at this. What happens if you put a stress on the product? Now that side is lower because there's more chemicals there. In order for that to undergo to go back to its to attain equilibrium again, some of that product has got to be converted to the reactant. So we say the reaction shifts to the left or to the reactant. Okay, it's going in the reverse direction. And that's exactly what happened until equilibrium's reattained. So any stress added has got to take that stress and move it to the other side so that equilibrium can be achieved. And you can visualize this using this analogy that I'm showing you. But basically, it's to make sure that that ratio gets back to that equilibrium constant. And the only way you're going to get back to the equilibrium constant when you have this is to decrease the amount of products and increase the amount of reactant. And physically, when you decrease the products and increase the reactant, that's reversing the reaction. That's reversing the reaction. So what happens when we have a deficit? When we have a deficit, that's like taking a reaction at equilibrium and removing the chemical. So now you have a deficit. Well, when we have a deficit, then the other side has to make up for that deficit, like this right here. Okay, so we're removing some reactant. We're physically or chemically removing that reactant. When we do that, again, we are not at equilibrium anymore. In order to get back to equilibrium, products have to make up that deficit. We say that the reaction shifts to the left, or reaction shifts to the reactant side. So again, we're controlling the direction of this reaction by either adding or taking away. In this particular case, if we want to favor the reactant side, we can either add more products or remove the reactant. Both will cause the reaction to shift to the left. So you have that. So you have that. What happens if we have a deficit on the product side? Well, if we have a deficit on the product side, then that means that the reactant has to make up for that deficit. And so we can say that the reaction favors the product side. Reaction shifts to the right or the product. Okay, shifts to the product side. It favors the product until equilibrium is reachieved. Once equilibrium is reachieved, then it stops. Okay, so changing concentrations allow you to manipulate the reaction to shift either to the left or to the right. Now, what happens? So this is basically it. Let's take a look at Le Chatelier's principle. We're at equilibrium right here. And then all of a sudden, we spike the reaction with more hydrogen. So that's the spike right here. That's the spike right here. So we want to observe what happens to the reaction as it tries to go back to equilibrium. Well, when we put a stress on the reactant side, it's got to remove that excess and convert it over to product. So that means that the amount of hydrogen you add is going to decrease. That's what you see right here. The amount of nitrogen that you had, because you didn't add any, is also going to be consumed. Okay? Even though you didn't add any nitrogen, it's got to go hand in hand with the hydrogen. It's got to be consumed. Otherwise, hydrogen will not convert over to ammonia. And then more ammonia will form until this new equilibrium is achieved. You've got a new equilibrium right there. And if you take these concentrations right here and put it in the mass action expression, and you take these concentrations right here and you put that in the mass action expression, it will give you the same number. That's the magic of K equilibrium. The concentrations at that equilibrium, the concentrations at that equilibrium will give you the same number, K equilibrium. That's the magic of K equilibrium, if you didn't change the temperature. Okay? So I want to make sure that you understand that in terms of what's going on pictorially in terms of that. So what happens if you change the pressure? Remember, I told you that there are three things that will cause the equilibrium to the reaction to shift one way or the other. One is concentration, the other is pressure, and the other one's temperature. So what happens when we have a pressure change? And the only way you're going to have a pressure change is when you decrease the volume. Why? Because when you decrease the volume for aqueous or gas, then you can change the concentration. Okay? So changing the pressure by changing the volume, remember when you make the volume smaller according to Boyle's law, you increase the pressure. Okay? So the only way to change the pressure for this thing to work is by changing the volume. Make the volume bigger, make the volume smaller. So let's take a look at this reaction right here. Again, ignore these right here. And this is the trick in making this analysis. Look for only chemicals that are gas. Only chemicals that are gas are going to fit this particular analysis. Both of these are gas. That's good. Now look, count the number of moles based on the balance equation. Here we have 1 mole. Based on the balance equation, here we have 2 moles based on the balance equation. 1 mole of N2O4 goes to 2 moles of NO2. So what happens when we make the pressure higher by making the volume smaller? Well, according to Le Chatelier now, we're causing a stress on that side because that side has more moles of gas. So that side's more sensitive to pressure. Okay, that side's more sensitive to pressure. So in order for, because we're increasing the pressure, in order for the pressure to decrease, we convert 2 moles of gas to 1 mole of gas. And so if we make the pressure higher, we're going to cause that reaction to shift to the left. But this is how you can figure it out based on that teeter-totter principle I showed you. Which side has more moles of gas? This side has more moles of gas, so I'm going to put P right there. The side with more moles of gas will have P, because that's the side that's sensitive to pressure. If they have the equal amount of gas, then no side is going to be favored. And changing the pressure by changing the volume is not going to favor either side. If you don't have any gas in your reaction, changing the size will not do anything because there's no gas involved. You have to look for chemicals in the gas phase, and then you look at their coefficient. Then you put a P where there's greater moles of gas. Now, let's take a look at this analogy in terms of pressure. Okay, let's take a look at this analogy in terms of pressure. Take a look at this right here. Oops. Okay, so again, we have our seesaw. All right, our seesaw here. This is N2O4. This is NO2. And what happens when we increase the pressure? We put a stress on that side because that's where P is found. We cause that teeter-totter to look like this. In order for this to go back to balance, more of the NO2 has got to convert over to the reactant side so that equilibrium is reachieved. So you look at the side that is sensitive to pressure. If that increases, then it's like putting stress on the product side because that's where we put P. And now increasing the pressure will cause this reaction to shift to the left. Okay. On the other hand, let me clear this up. Let's say that we have a reaction, A plus goes to B. And let's say there's 2 moles of gas here, and there's only 1 mole of gas here. So again, we have A going to B. We want to put P on this side. Why? Because that side is more sensitive to pressure. That side's more sensitive to pressure because it's 2 moles of gas to 1 mole of gas. So when we increase the pressure here, we cause this teeter-totter to look like this. This reaction, in order to go back to equilibrium, will favor the forward direction. More moles of A will convert to fewer moles of B, therefore alleviating that pressure, and the reaction shifts to the right. On the other hand, if we remove the pressure, again, that's why I like the teeter-totter analogy. Okay, this is A, this is B, and this is 2A going to 2B, and this is P. But we remove the pressure, then the teeter-totter will look like this. And in order for this thing to go back to balance, more of the B has got to convert over to A. For every 1 mole of B, you get 2 moles of A. That will give you a larger pressure. So when you have a pressure deficit on the reactant, the few moles on the other side will convert to more moles on that side, and say we can say that the reaction shifts to the left. It's this teeter-totter analogy. When we have a deficit, that side goes up. When we have a stress, we're putting a stress here, that side goes down. Le Chatelier tells us it'll eventually come back to equilibrium. It will eventually. And the way it goes back to equilibrium is that the chemicals have to either exchange side, either one chemical goes to the other or one of the other chemical goes to the other, so that now you get that balance. You get that balance. So let's take a look at this right here. And again, ignore this. If I ask you, this is a balance equation, and you guys can just put it in the chat, okay? Which side is sensitive to pressure? Is the reactant side sensitive to pressure, or is the product side sensitive to pressure based on this balance equation? So if you guys can just do that, that way I know you're listening and not off into space, okay? So someone said reactant. Anyone else? Okay, someone said product. Okay, I'll accept at least 2 of you. Let's count the number of moles. These are gas. This is 2 and this is 2. So that's 4 moles of gas on the reactant side. These are gas. And this is 2 and this is 5. So there's 5 moles of gas on the product side. So the side that's sensitive to pressure is the product. Okay. The side with more moles of gas is going to be the side that's sensitive to pressure. Now we can say, what happens to the pressure if the volume is decreased? When the volume is decreased, the pressure increases. Okay. What direction will the reaction shift? If you decrease the volume, if you decrease the volume, the pressure increases. You're putting a stress on the product side. We can say that the reaction now is going to shift to the left, because what's going on is that the product has pressure on it. This is reactant. let's say that this is A, this is B. It's got pressure on it. When we apply more pressure, the teeter-totter will look like this. As we apply more pressure, the only way for that thing to get back to equilibrium is more of the B, more of the more moles of gas have got to convert over to fewer moles of gas. The fewer moles of gas will have less pressure. So we can say that the reaction shifts to the left. Okay, we can say the reaction shifts to the left. And so that's basically how you want to answer that question. Okay, pressure increase, here it is, pressure increase. And what's going on is the reaction shifts to the left for that particular case. So again, you can use this teeter-totter analogy to make that analysis. Let me clear this up real quick. Okay, what happens to the pressure if the volume increases? When the volume increases, then you've got more space, the pressure decreases. When the pressure decreases, it's like removing the product side because that's where the pressure is. So we can say that when we let the pressure be lower by making the volume bigger, the reaction is going to make up for that deficit. The fewer moles of gas on the reactant side will convert over to more moles of gas on the product side to make up for that deficit in pressure. Okay, so that's what you have right there. Pressure decrease, reaction shifts to the product side. And here you can see the teeter-totter where the pressure decreases and the reactant has to make up for that deficit. The reaction shifts to the right. Okay, reaction shifts to the right. Let's take a look at this right here. Let's take a look at that. And if you look at this equation, you're going to see that this is a balanced equation again. Count the number of moles of gas on the left. This is one, so there's 2 here. And there's 2 here. So the moles of gas are equal on both sides. This is not sensitive to pressure. You change the volume, by decreasing it or increasing it, nothing's going to happen. Nothing's going to happen. And so that's what happens. No shift. Okay. No shift as well. Because the moles of gas, and you're only looking for moles of gas, are the same in both sides. That's key. Let's take a look at this next problem. Okay, again, you can ignore this. Okay, you got carbon monoxide producing carbon solid and carbon dioxide. And this is a balanced equation. 2 carbons on both sides, 2 oxygens on both sides. Okay. Which side is sensitive to pressure? And if you, and again, the key here is to look only for the moles of gas. Okay, moles of gas. So if you look at this right here, you've got 2 moles of gas right here, 2 moles of gas. This is a solid. It's not gas, that's a solid. You've got 1 mole of gas here. The mass action expression for this, by the way, would be this. You leave out the carbon because it's a solid, okay? So for this reaction, you would put P on the reactant side because there's more moles of gas there. Even though both sides have equal moles, there's 1 mole of carbon, 1 mole of carbon dioxide on the product side. Only carbon dioxide is a gas. That's the only one you count. So the product has 1 mole of gas, the reactant has 2 moles of gas. And so what happens when you decrease the volume, you increase the pressure, you're putting a stress on the product side, you're going to cause that reaction to shift to the right. And that's what you see right here, okay? That's what you see right here. You're putting stress on the reactant, you're increasing the pressure, the reaction is going to shift to the product side. What happens when you increase the volume, you decrease the pressure, you're causing a deficit on the reactant side. The reaction is going to make up that deficit by causing more of the reactant to go over to, more of the product to go over to the reactant. Okay, until you reach an equilibrium. By the way, let's go back here. What happens if I increase the pressure by adding, say, argon? Argon is an inert gas, but I'm going to, these things are all in a chamber, and I'm going to increase the pressure by adding more argon in that chamber. what happens to the equilibrium? You guys should say nothing. Why? Because the equilibrium is only going to be affected by those chemicals in the mass action expression. And the chemicals in the mass action expression are carbon dioxide and carbon monoxide. Argon is not in the mass action expression. So yeah, we can change the amount of gas, the pressure in that chamber, but we're not changing the moles of carbon dioxide or the moles of carbon monoxide, and so nothing's going to happen. So when you add an inert gas in a reaction which has gas, nothing's going to happen. If you add a catalyst, nothing's going to happen, because a catalyst is not in the mass action expression. Only chemicals in which the concentration or the partial pressure in the mass action expression changes are going to cause that reaction to shift to the product or the reactant side. Okay, so I hope that that's clear. Let's take a look at the last effect. That's temperature effect. Okay, the temperature effect. Let's skip this part right here. This is actually the mathematics of why these things will shift. But let's take a look at temperature. Temperature, remember I told you when you have an endothermic reaction means that the energy is a reactant. When you have an exothermic reaction, then we say the energy is a product. And so what we can do is, depending on what the energetics is for that reaction, we can put E either as a reactant or a product. And now we can use our teeter-totter analogy. If we add more energy for an endothermic reaction, we're putting more stress on the reactant. The reaction should favor the product because we're putting more stress on the reactant. If we have an endothermic reaction and we're removing energy by cooling it down, then there's a deficit on the reactant. The product has got to make up for that deficit, and so the reaction should shift to the left. So first determine whether energy is a reactant or a product. Determine whether the reaction is endothermic or exothermic. Then you can use our teeter-totter analogy to predict which way the reaction will shift, depending on whether you're heating up the reaction or cooling down the reaction. Okay, so that's what I'm talking about right here. This just introduces exothermic and endothermic. So let's take a look at this right here. Let's take a look at the endothermic reaction and what happens when we increase the temperature for an endothermic reaction. Well, we're putting a stress on the reactant side. Remember, endothermic energy is a reactant. In order for this to go back to equilibrium, we have to take the reactant and move it over to product so we get back to equilibrium. So for endothermic reaction, if you increase the temperature, you add energy, you're putting a stress on the reactant side, it causes that side in the teeter-totter to be heavily weighted. In order for that to go back to equilibrium, the reactant has got to shift over to product until you get a new equilibrium. Okay, that's why you need to know where to put energy. Is it on the reactant or the product? And now we can use this teeter-totter analogy. What happens when, so here's a reaction, and you can see here that I have plus E. So right away, you know that energy is a product. Energy is a product. So in which direction, if you decrease the temperature? When you decrease the temperature, it's like removing energy. You're lowering the temperature, you're removing the energy. So there's a deficit on this side. There's a deficit on the product side. If there's a deficit on the product side, you guys know that that side's going to get higher because it's going to be lighter. Therefore, how does that get back to equilibrium? The reactant has got to make up for that deficit. And that's what you see in, well, I don't show the diagram, but you can see right here that if you decrease the temperature, then the reaction shifts to the right because there's a deficit on the product. So more of the reactant has got to make up for the deficit on the product. The reaction shifts to the right. If you increase the temperature, that's the second part right here, okay, then there's going to be a stress on the product side. This is an exothermic reaction. If there's a stress on the product side, then that side gets heavily weighted. In order for the equilibrium to be re-achieved, more of the product has got to return back to reactant. And so we say the reaction shifts to the left. That's exactly what we see right there. Okay. Another way of expressing energy is telling me that the energy is positive or negative. When it's positive, it's endothermic. Endothermic. Energy is a reactant. When it's negative, it's exothermic. Energy is a product. So here it's positive 120. That means energy is on this side. Energy is in the reactant side. So what happens when I decrease the temperature for a reaction in which it has positive 120 kilojoules? Well, when I decrease the temperature, it's like removing the reactant. If I have a deficit of the reactant, then the reaction shifts to the left. It has to make up for that deficit. The reaction shifts to the left. On the other hand, if I increase the temperature, that's putting a stress on the reactant side, because this is an endothermic reaction. If you put a stress on the reactant side, it's got to remove that excess and move it over to product. Reaction shifts to the right. Okay. Again, your teeter-totter, you're putting a stress on the reactant side. So you're going to have more weight. You're going to have more weight. This reactant, this is a product. This is energy. It's going to look like this. You're putting a stress here. The only way for that thing to get back to equilibrium is more of the reactant. It's got to convert over to product until you get back to equilibrium. We say that the reaction shifts to the right. The reaction shifts to the right when we increase the temperature for an endothermic reaction. And finally, let's take a look at this. Well, this is an exothermic reaction. So there's 3 different ways to express energy. We can put E either on the product or the reactant. We can say delta H is positive or negative, or we can say that it's exothermic or endothermic. Exothermic means that energy is on the product side. And when we decrease the temperature, we're causing a deficit on the product side. The reaction will shift to the right to make up for that deficit. If we increase the temperature, we're putting a stress on the product side. That stress will cause that product side to convert over to the reactant. The reaction shifts to the reactant side right there. Okay, so that's how you analyze reaction based on Le Chatelier. Le Chatelier basically gives you a working guide as to predicting the reaction behavior because of changes that you've done to a reaction at equilibrium. You're basically manipulating the reaction to either favor the product or the reactant. Okay, I've got to go now, but the rest of these just kind of summarizes what I talked about. Okay, the rest of the lecture note, but you've got the main point in the lecture notes in terms of Le Chatelier's principle, what equilibrium means, what equilibrium constant means in terms of that context. Okay, and hopefully this chapter is a little bit more clear after our discussion, because it's about manipulating, it's about the speed by which the reaction reaches equilibrium. It's also about the efficiency of that reaction.